So we know how carbon creates stable bonds, right? But let's dive deeper into how more diversity is created with carbon specifically. So I know that, of course, everything is kind of all over the place. You want to just make sure that you're orienting yourself and organizing yourself with this information. Sometimes I give a little bit too much, sometimes I don't give enough. But the goal is that I'm making sure that you are getting the most important portion of these, of this chapter, for example. Now, when it comes to diversity of organic molecules, it's all about carbon's ability to bond to itself first. And of course, carbon's ability to bond to hydrogen. That's like the main important thing. And guess what? When you have carbon molecules and only carbon attaching to itself and hydrogen, that here, carbon attached to another carbon, attached to another carbon, fluttered with nothing but hydrogens. And what I mean by fluttered with nothing but hydrogens is that I'm saying that it is basically saturated with hydrogen. All of the bonds available to carbon are going to it being attached to another carbon and, of course, all the other hydrogens. And these are called hydrocarbons. And they definitely are the basis for what we understand when it comes to diversity of organic molecules. We're going to be taking these hydrocarbons and adding things to them. What that really means for us is you're going to be substituting these carbon-hydrogen bond out. So instead of this carbon-hydrogen bond being here, let's say it's being substituted for a carbon-oxygen bond. Well, when you substitute that carbon-hydrogen bond with a heteroatom like oxygen, nitrogen, sulfur, any kind of halogens, for example, you effectively are going to change the structure and function of the organic molecule. Because guess what? When you change the structure, you change the function. That's it, okay? And that's going to happen throughout biology, organic chemistry, etc. You change the structure, you change the function of the molecule. And this is basically going to create brand new families of organic compounds with all these different properties, often called functional. And so for us, again, we're going to be seeing these functional groups. We're going to be learning about 8 of them. Of course, the hydrocarbons themselves can be considered a functional group in organic chemistry, and you'll learn about that when we get into an organic chemistry course. Okay? So, why are functional groups going to be the most reactive? Well, these carbon-hydrogen bonds, carbon-hydrogen, and then carbon-carbon, they actually are pretty unreactive. Okay? They're actually non-polar bonds, so they're not really that reactive. And because they're not that reactive, when you have carbon attached to a heteroatom, for example, that's when you're actually going to get that polarity. And so what does reactivity really mean? It means a shift in electron density. So we know if the electron negative energy goes to one side more, now I've created a partially positive charge, right? We have an electron density here. We know if we have the electron negative energy more over here for that charge, it's going to be more partially negative, and then this will be partially positive. So because of that shift in electron density, you're going to get something that's reactive. Think about carbon and oxygen. Oxygen is more electronegative. So oxygen is going to want way more affinity for the negative actual energy, of course, charge from the electrons themselves. So because of that, you will definitely have more polarity, which also is going to give more reactivity. Also, think about them reacting, organic compounds reacting to acid and bases. So everything you're learning about inorganic compounds, you can learn about organic compounds as well. And of course, when you get into an official organic chemistry course, you'll get into more detail. So because a lot of organic compounds focus on structure and function, we saw how carbon's structure can dictate its ability to bond. That's what it's all about. Let me go ahead and show you all these examples here. Okay, so we have our carbon, we have our carbons here, carbon and carbon attachments, carbon hydrogens. These are all going to be our hydrocarbon portions of these organic compounds. So now we're thinking, okay, we have hydrocarbon, we can add things to it. So that means there's always going to be some kind of hydrocarbon component. Okay, folks? And so when it comes to organic compounds, again, when you add different heteroatoms, add different halogens, add different groups, you effectively change that structure. Okay, folks? And because so many organic compounds are really made up of carbon, hydrogen, carbon, hydrogen, carbon, hydrogen in certain amounts, right? Or really carbon-carbon bonds and carbon-hydrogen bonds, a lot of times these hydrocarbons will get the generic symbol R. Okay, they're not a part of the reactivity, but they are a hydrocarbon that's a part of this organic compound. And so when you're looking at these functional groups, and sometimes again they're called families, you'll see an R group here, which represents that yes, it's an organic compound, because we know it's made of carbon-hydrogen bonds and also a bunch of carbon-carbon bonds. So this is kind of the hydrocarbon area. So the hard part is like you don't want to have these ginormous compounds and then keep on having to write the entire CH. Sometimes you just want to just say, here's the R group. Let me focus on the thing that's actually going to cause reactivity. So a lot of times with these general formulas for the functional groups, you'll see they just have R groups and then whatever elements in the middle or a part of the actual functional group here, that's going to be the part that is included in any of the bonding. Okay, and so we're going to be going through and learning about all these different functional groups in the next section of videos. Okay, actually, we're going to learn about the 8 families of the organic chemistry mafia. Okay, learn about hydrocarbons and all that kind of stuff and get more detail. But this is just kind of helping you understand why carbon is so diverse. Okay, now let's look at this ginormous chemical over here. We have all of these potential functions, right? And this is only a small amount of them. We have all these potential functions here. And we have so many different arrangements of carbon that the diversity of organic compounds is just crazy. Right? There's like 19 million in counting, of course, there's even more now. So let's look at this compound here. We have a ring here, we have double bonds, we have a triple bond, we have oxygens. So we know that this structure definitely has some reactivity available. We have nitrogens here as well. And then we have those good old hydrocarbons, R group portions. This will be an R group. This can be considered R group as a bunch of carbon hydrogens, but it does have things attached to it. So it might be a part of the main portion of how to name it. Our goal when we're learning about the diversity of organic molecules is to learn about the simplest ones first, the simple families, and then keep on adding things to them like oxygens or nitrogens and seeing how that definitely changes the function and what they can do. And of course, a lot of times when we're thinking about large things like medicines, like acetaminophen, for example, pain relievers, they're just ginormous organic molecules. And so imagine how fun it would be to be in a lab and just be adding so many different reactive properties to see how they can help with drug design or even help with curing different portions of cancers. I mean, get into the details of it. I always recommend that if you find something that you're interested in, go ahead and try it out, right, folks? So these functional groups become very important. And functional groups and families sometimes are interchangeable in organic chemistry, so I'll do my best to help you distinguish. That's really the goal. For me, a functional group is a portion of a molecule that is recognizable on that organic compound. And of course, that makes it more reactive, which creates different families. So because there's an OH group here, that's going to create a different family called the alcohol. Anytime you have an OH group, you know there's an alcohol-based portion on that molecule. Okay? When you see a functional group on a molecule, of course, the same functional group in the same molecule, that usually behaves the same way. So it's not like, oh, I see alcohol in the molecule. That means if I see alcohol in another molecule, it's going to be different. No, the alcohol portion on that molecule are going to behave the same way. Okay? And there's definitely several families. Like I only talked about the 8 that we're going to be getting into, but there's a few dozen organic chemistry families, and they're all going to be arranged based on structure and of course reactivity from these functional groups that are attached to it. Okay? So all we need to do is start figuring out ways to start distinguishing all this work. And also, we got to start by figuring out how do I actually read some of these structures that I see here. All right, folks, let's get into it.